Thank you for the introduction. So I have the honor to be the last presenter. Thank you for staying here until the end. I'm here to talk about calcium phosphate recovery in anaerobic treatment of black water.
Ja, dat zeg ik. Ik ben ook stil worden.
Other button?
Toen ze begon.
Okay, perfect. So I'm talking about the process where we can recover both energy as methane and phosphorus as calcium phosphate in one anaerobic reactor operated on black water. So this is opposed to the conventional process where we are recovering struvite that actually has a lower economic value than calcium phosphate in another step after the USB reactor. Okay. About a year after we started our black water USB reactor, a miracle happened. For the first time, under these conditions, we were able to biologically induce the precipitation of pure calcium phosphate granules. And here in the picture A, you see these granules in the reactor covered by a biomass layer. And in the picture B, you see these granules separated from the slash fed, rinsed and dried, having a diameter of 1 to 2 millimeters and organic content of 30 weight percent. And when we then burn away the organics, we are left with these white calcium phosphate granules of similar diameter. I found these granules both at lab and demo scale reactors operated on the same black water. And here is the elemental composition of these granules. They are mostly composed of calcium and phosphorus, only traces of magnesium and potassium, so we can say that there is no struvite precipitated in those reactors, so those granules. And they have a molar calcium to phosphorus ratio similar to the one of hydroxyapatite, which is the most crystalline phase of calcium phosphate, and to amorphous calcium phosphate, which is the most soluble calcium phosphate, also the initial phase, and to octocalcium phosphate, which is the sort of the transient phase in the development of hydroxyapatite. I also did elemental mapping on the thin slice section of these granules. So on the left side you can see the calcium levels, and on the right side you see phosphorus levels. So the blue color indicates low concentration, and the yellow or the red color indicates high concentration. So what we can first see that the organic fraction I was telling you about is mostly concentrated outside the granules, indicated by the blue ring around the granule. And secondly, we can also find that within the relatively evenly distributed calcium phosphate matrix, we are able to pinpoint really small separate clusters of calcium carbonate, indicated by really high calcium concentration, but absence of phosphorus, and these are indicated by the red circle. And in fact, the presence of these separate calcium carbonate crystals could be the key factor why this calcium phosphate precipitation occurred, and why it in these granules, since the presence of seed crystals really significantly reduced the energy needed to nucleate, and therefore really induce the precipitation. However, the carbonate content of these granules is less than 5%, so we still are left with relatively pure calcium phosphate. I also analyzed the precipitated species in the granules with XRD, Raman, and FTIR. And they all showed the coexistence of 3 different kinds of calcium phosphate phases: hydroxyapatite, carbonated hydroxyapatite, and calcium phosphate hydrate. So if we want to reuse these calcium phosphate granules as a new phosphorus product, so for example fertilizer, the phosphate content and the heavy metal content are of importance. And here I compared the granules from both lab and demo scale with other phosphorus recovery products and with phosphate rock and a very common phosphorus fertilizer, triple superphosphate. And I found that the phosphate level is similar to these other phosphorus products, and the heavy metals are either lower or similar to the other phosphorus products, meaning that it could be very well used as a new fertilizer, for example. The only heavy metal that was higher than the other phosphorus products is copper, and I'm working on pinpointing the origin of copper in black water. Okay. So with this,
Het is nog nooit gelukt bij niemand.
The system style.
okay, this one. Okay, so with this process we can simultaneously recover both phosphorus and energy in a black water USB reactor. So we can recover similar amount of methane compared to the process without granules indicated in the brackets. And we can significantly increase the biomass concentration in the reactor, since microbes like to attach on these inert particles and grow into dense granular sludge. And this way we can further save energy in the reactor configuration. And without any addition of chemicals, we are able to recover calcium phosphate at least 16 grams phosphorus per person per year, but this is really the minimum amount that we are at the moment practically able to harvest from the reactor. And this is really a small fraction of the total amount of inorganic phosphorus in the reactor, so I'm at the moment determining the maximum potential to recover these calcium phosphate granules. I would like to thank you for your attention. Sorry for the technical problems. And
Finally.
oh, there was a. Could you put the last slide?
Okay.
So finally, I would like to invite you all to Wageningen. In 2015, we will have our 50th anniversary symposium. So please join us.
Nee. Can always the front row.
Thank you for your presentation. So, Sir Lyon, NRC Montreal. So, if I understood correctly, your main compound is hydroxyapatite, right? And I mean, hydroxyapatite is I think it's a high-value product. It's used as artificial bone, medical you'll find a term, or dentistry, and artificial bone. You think there could be a market, that could be a market for you, calcium phosphate granule, in that sense?
Even for medical industry?
Yeah.
Yeah, I'm not really sure because it doesn't have organics in it, so of course the purity has to be really high for medical industry. But of course, maybe in the future, if we are really able to separate the organic and the
Anna Sars from Oxford University. Really nice presentation, thank you. I was wondering if you have a little bit more information about the mechanisms around the calcium phosphate information. Currently we're working with material that can produce stratified crystals, but those are in aerobic conditions. So I was just wondering if you could comment on that.
Yeah, of course it's a really complex process and we are just sort of starting to really unravel this phenomena. But I think it is a combination of course, biological, chemical parameters, that there is a supersaturation of calcium phosphate in the reactor, and then the role of biomass encapsulating calcium phosphate, and in that sense, creating a microenvironment for the precipitation of, and the dominance of calcium phosphate rather than calcium carbonate or fluoride in the biofilm. But we are still working on it.
I had more or less a similar question.
Okay.
In the past, we did some research on calcium carbonate formation in USB reactors, was also involved with it. And what we noticed that the precipitation constants, for instance in calcium carbonate, dropped considerably by a factor of 100 to log units when phosphate was present in excessive amounts. And that idea was picked up in the paper mill, where they fed with phosphorus acid as nutrient to prevent calcium carbonate precipitation inside the anaerobic reactor. So everything was done in the aerobic reactor. So it's very good if you, with OLI or another type of chemistry program, but then you have to check the K values, because you cannot take the K values from the tables. They change completely.
So what was your question?
In response to the question over there, so a possible explanation why calcium carbonate is not formed and calcium phosphate is formed, because the K of calcium carbonate is dropped down under the presence of phosphorus.
Okay, yeah, exactly. Yeah.
Okay, thank you for you.